Yes, hello. Is this audible to you people?
Yes, yes.
Uh, Okay, so we had completed with Kirchhoff's law in the last class. Now, potentiometer is not included in your board syllabus, but we'll just do it in briefly because meter bridge and potentiometer, these are a part of your entrances and that it can come and you should have an idea about it. So we'll do it in briefly. That's why I've written most of the things prior. So just let's discuss it quickly. Basically, it's a device that is used to measure the exact EMF or potential difference. So how is it constructed? You have a wire. Let's say this wire is AB. AB wire is there. This is AB wire. We call this as the potentiometer wire. Now, we connect it to a circuit with a cell. This is the cell has an EMF E and an external resistor capital R. So this is known as the driving cell. Now, if you have an unknown cell, then the EMF can be measured with the help of this potentiometer. Now, what is the principle of potentiometer? It says that whatever is the potential difference, across whatever is the fall in potential difference, that potential difference is directly proportional to the length of potentiometer wire. This is the basic principle of potentiometer. And it's a device that is used to measure EMF. So we'll see the applications also briefly. What are the applications? Before that, a very short theory portion that is very easy to understand is the basics or the basis principle of it. That includes that only. Fall in potential difference is directly proportional to the length. Let's say small r, this is the resistance of potentiometer wire. Resistance of potentiometer wire. After this, we'll discuss identical cells. If you remember, cells we have already discussed. Equivalent EMF, equivalent internal resistance. Now we'll see if all the cells are identical, then how to deal with it. So just first look at the potentiometer, then we'll discuss it. So this is the resistance of the potentiometer wire. What is the potentiometer wire? Potentiometer wire is that wire only, AB, which I was mentioning you. That wire that is connected, that wire AB. So whatever is the current across it, whatever is the potential difference across it, that is measured. So current will be what? See, EMF of the cell is E. Resistor, external resistance that is connected. External resistance that is connected is capital R. And the internal resistance of the wire or the potentiometer wire, that is small r. So this is the value of current. So potential drop or voltage drop across the potentiometer wire will be what? Current is capital I. Resistance of the potentiometer wire is small r. So potential drop becomes I multiplied by small r, which can be written as E by R plus R multiplied by R. Now, one more thing here you have, which is known as potential gradient. So potential gradient is not a new topic for all of us. We have studied potential gradient when we were discussing electric potential and capacitance. There we had discussed that electric field is directly proportional to the potential gradient. So potential gradient, I'm again repeating, if anything gets divided by time, anything is per unit time or it gets divided by time, we call it rate. Like rate of change of displacement, this is known as velocity. Rate of change of displacement is known as velocity because distance gets divided by time. Similarly, if anything gets divided by distance or changes with respect to position, then you call it as gradient. The way we have potential per unit length. Potential per unit length or potential changing with respect to length, then we call it as potential gradient. So in case of potentiometer, it is represented through the symbol K. This is known as the potential gradient. It's just the method to represent it. The definitions of potential gradient remains the same. Potential gradient is potential per unit length. So you can even write potential from here. VAB, potential across this wire. This is E by capital R plus small r multiplied by R. VAB from here divided by capital L. We'll do one numerical on this also. Easy formula based numericals, and then we'll see all the three applications of it. So then we can shift on to the identical cells portion. So just note it down before that. Your test papers, let me discuss that. So many of you have attempted that test. Hanifa, you were absent in the previous class, no?
Yes, I had a flight, so I couldn't attend.
Okay. Sarah is there? Sarah is there. So yes, Sarah's paper 10 on 10. Then Akifa is in this batch. Akifa is there. No, Akifa isn't here. Hanifa didn't give the last test. She was there in the previous one. Okay. Fatima gave. Fatima, you had committed a very, very slight error in your calculations. 10 to the power minus 17. It had to be 10 to the power positive 17. See, when this denominator 10 to the power minus 19, and here you have 10 to the power minus 2, this becomes 10 to the power 17. So slight errors you have committed. Rest of the paper was fine. And who was there? Krishna was there in the last class. Again, same mistake, Krishna. 10 to the power minus 17. Fatima Munir, has she come today? Oh, okay, Fatima Munir. Yeah, her paper was fine. Perfect. Hamza is in this batch, no? This is your paper, Hamza. Again, very slight error in the powers of it. So half mark got detected over there. Atif is in this batch. Yes, calculation mistake by Atif, no? I believe. Yes, calculation mistake. Again, same mistake, calculation mistake. All of you have just committed errors in the calculation part. Hiba gave the test. Hiba gave the test. Hiba, one more thing. All of you, I wanted to discuss this as well. Whenever you are giving the answers, always mention the units. Like current density. Current density is current divided by area. So that is what? That is current, that is ampere divided by meter square. So ampere per meter square, specify that. And don't leave your answers like this. 2 into 10 to the power minus 17 divided by 1.6 and all. Otherwise, you can simply directly lose marks. It's better if you solve it. And in the derivation, as I told previously, so many students did the derivation perfectly this time. But again, tau average has not been mentioned, initial velocities average has not been mentioned. So mention all those things as well. Whatever we have written, no, we had taken all the average relaxation time and then we had equated it to tau. That represented the tau. So always take those things. Otherwise, the rest of the thing was fine. Kulsum is also there. Is she present, Kulsum? Kulsum is there. Okay, so Kulsum is 10 on 10. Huzefa couldn't give the test. Okay, this many students. Okay, you people note this down. So most probably this will be our last class of current electricity. And then maybe it can happen that 15 to 20 minutes of the next class will be used in the completion of this chapter. Otherwise, we'll be starting with chapter number 4, magnetic effects of electric current, from the next class onwards. All right. Did you write this, all of you?
Yes, ma'am.
All right. Let's do a very easy numerical on this. See, EMF of the cell is given to you as 15 volts. External resistor which is connected, that is given as 5 ohms. Now, this is the potentiometer wire. This AB which you are able to observe, this is the potentiometer wire. The distance or the length of the potentiometer wire, this is given to you as 10 meters. And the internal resistance, or you can say resistance of this wire, potentiometer wire, this is 5 ohms. Firstly, you have to find out current in the wire. So I'll give you time to write it down. Firstly, let's discuss the solution of it. So current is what? Current is EMF, that is divided by the external resistor plus the resistance of the potentiometer. Okay, Fatima, what is the EMF given?
15 volt.
15. Perfect. So EMF, this is given as 15. Okay, Josefa, what is the external resistor given to you? See, look in the figure. Resistor which is connected. What is the value of resistor? Josefa? It's 5. Good. That is 5 ohms. External resistor is given as 5 ohm. And small r is the resistance of the potentiometer wire. Krishna, what is this value of small r? Yes, Krishna? Resistance of potentiometer wire.
5 ohms, ma'am.
5 ohms. 5 ohms is given. The resistance of the potentiometer wire is also given as 5 ohms. It is mentioned in the question. See, 5 ohm is already given to you. So this completes our answer. We have the value of current as what? 15 divided by 10, which is 1.5 amperes. This is the answer of the first part. Second part says what? Voltage across the potentiometer wire. Voltage across the potentiometer wire means VAB. VAB is the potentiometer across the voltage across the potentiometer. So that is current multiplied by the resistance. Current is what? Current we have calculated, that is 1.5 amperes. And resistance of the potentiometer wire, as rightly said by Krishna, that is 5. So this gives us 7.5 volts. Third part is potential gradient K. So K is what? VAB divided by L. VAB is the potential. VAB we have already calculated in the second part, divided by the length. So yes, who is going to answer this? Atif, you tell us what is VAB and what is L? VAB first. What is VAB? Okay, Atif, fine. Yes, Fatima, what's the answer coming?
Teacher, that's not the answer. That's VAB.
Okay, VAB. VAB is 7.5. Yes, VAB is 7.5. See, from the second part we have calculated VAB is 7.5. Length of the potentiometer wire is given to you as 10. Exactly. So your potential gradient comes out to be what? 7.5 divided by 10, that is 0.75 volt per. All right, note down this question as well. Done?
Done, ma'am.
All right. So now let's not discuss any numericals further. Let's discuss directly the three applications that I was mentioning to you people. Now, see, there are majorly three applications of potentiometer. First one is the measurement of EMF. Now, one EMF is already given to you. You must have seen in the circuit, capital E that we were considering. That is already given to you. Now, you have to find out the EMF of an unknown cell. That is the application, first application of potentiometer. Second is comparison of EMF. Means if you have two cells and you have to find out their EMFs or compare their EMFs. Then third one is the measurement of internal resistance. So internal resistance, the formula is enough for you people. So let's just discuss the first one first, measurement of EMF. See, till here you people are aware of capital R is there, capital E is there, and this is the potentiometer wire. A. Now here the cell is connected with a galvanometer, and if you people have had your practicals, then you must have seen through this galvanometer a jockey stick is connected, and you hover over the potentiometer wire, complete wire, like this. There's a small jockey stick, very small, like this pen, and you just scroll over it, over it, and wherever the galvanometer does not show any deflection, there you mark it as the null point. So this is called the null point. So the length is L. Let's say L is the length, that is the null points. Then what happens, basically current stops flowing, means all the potential on the left side of the potentiometer becomes equal to the right side. Let me write this first. Corresponding to the null point, the current through the galvanometer this becomes zero. Basically, whatever is the value of voltage on the left side of the potentiometer, means across this null point, that becomes equal to the right hand side. Again, voltage or EMF is given by the principle only. What did I tell you about the principle? Voltage is directly proportional to the length of it. So EMF, let's say E is equal to KL. K is the constant that we get, which we call as the potential gradient. Now see, there are two conditions which you should remember. First one, if the EMF of the unknown cell, this is lesser than the EMF of the driving cell, then we say the condition is not a balanced condition. The condition can be balanced. This is known as the balanced condition. Means you will get the null point if this is the case. But if your capital E is greater than your EMF of the driving cell, then we say cell cannot be balanced. Cell cannot be balanced. Now, what is capital E and small e? Let me write it, because a few people will then forget this. This E is the EMF of the driving cell, which has to be greater than the EMF of the unknown cell. So this is the first application of it. So quickly note it down, then we'll discuss the second application. We won't do any numericals. Numericals, you people will be able to handle it. If you people require it, then we can do numericals. There's no issue. Just quickly note down these points of first part, then we'll discuss comparison of EMF. Now the second application is comparison of EMF, two EMFs if you have. So this involves comparison of EMF. This is one cell with an external resistor. This is the EMF of the cell. This is the potentiometer wire. AB is the potentiometer wire. Now, first cell has been connected in the previous manner, the way we have seen the above case. Then another cell has been connected with the galvanometer, and it will give you the deflection at another length, because different EMFs have different values of length. That's why we see, the principle of potentiometer is what? That the potential is directly dependent on the length. So let's say this is E1 is the potential difference of the first cell, E2 is the potential EMF of the second cell. So how to compare it? Comparison is very easy. E1 will be equal to what? Let's say L1 is the length that we are getting. So E1 will be equal to KL1, E2 will be equal to KL2. Now take up the ratios. If you take the ratios, KK will get cancelled. E1 by E2 will be equal to L1 by L2. This is the second application of comparison of EMF. All right, so note this down as well. Then we'll do the last one, internal resistance. Then we can move on to your identical cells topic. Yes, Atif, I'll show you. This was the first case that we have done. The numerical you have seen, no, Atif? You were there, no?
Yes, teacher.
All right. Josefa, Emma, do you realize that your camera is open for past 15 minutes and we people have been observing you? How much do you pay attention in the class and how much do you use your mobile phone?
Yes, teacher, you can scroll down.
Now the measurement of internal resistance. So how to calculate the internal resistance? See, the rest of the circuit remains the same. EMF of the cell connected with an internal resistor. Then there you have the potentiometer wire. We are naming it as AB again. And then the cell, unknown cell, which is connected. There would be an internal resistance of this cell. Now we are finding out the internal resistance of this cell. This is small r, which we are trying to find out over here. Internal resistance of cell. So let me just clear it. This is the internal resistance of cell. There a galvanometer has been connected, and then you get again a null point. Let's say C is the null point where you hover over the potentiometer wire and you get it. Now see, in order to calculate the internal resistance, you have to have few things: external resistor of the circuit as well. This external resistor is of the potentiometer wire. We need an external resistor for this internal resistance calculation. So let's say we have connected capital R as the internal resistance, key is there, and we have formed the whole circuit over here. Now how to calculate the internal resistance? First, the EMF will be what? EMF will be directly equal to KL1. L1 is what? L1 is the length. L1 and L2, these are two lengths. Let's say this is L1. L1 is the balancing length with key open. This is the balancing length when the key is open. And let's say L2 when key is closed. We need two lengths right now. L2 is the balancing length when key is closed. Now we have to balance both the voltages that occur on the right and left hand side. For example, voltage was what? The formula was E divided by R1 plus small r multiplied by capital R1. R1 I have just taken in order to distinguish between the external resistor that is connected in the main circuit and the external resistor that is connected in this small circuit that is formed. So R1 I have taken to distinguish it from the main circuit, means the potentiometer wire circuit and this small circuit that has been connected. So this is the first voltage. This is equal to what? Voltage is directly proportional to the length. So when your key is closed, it will be KL2. So you have two equations with you. First equation is what? This is your first equation. E is equal to KL1, and this is your second equation. Now take the ratios of both the equation. E R1 plus small r multiplied by R1 is equal to KL2. And here you had E is equal to KL1. See, EMF got cancelled, KK got cancelled. This derivation you people need not learn. It's just that if I write directly the formula, then you won't be able to understand how did it come. So that's why we are just doing the derivation in. We have to find out the small r. See, L1 by L2 will be what? The reciprocal of this, L1 by L2 will be R1 plus R divided by R1. See, if I separate R1 by R1 plus small r by R1, if I separate these terms, there won't be any effect in the answer. So R1 getting cancelled, this is 1. Small r will be equal to what? Ultimately, small r will be equal to L1 by L2 minus 1 with the resistance, external resistor that is connected in the new circuit. All right, so this is the formula that is used. So these are the three applications of potentiometer: calculation of EMF, comparison of EMF, and calculation of internal resistance. Internal resistance and EMF, both these things are found for the unknown cell, not the driving cell. For the driving cell and the whole circuit, we already know that we are given. So noted from here, measurement of internal resistance. Then we'll jump to identical cells topic. That will be the last topic for your current electricity. Just text me done in the chat box when you people have written it. Okay, then let's start with combination of identical cells. All right. Now, series combination of identical cells. Identical cells means what? If all the cells are which are connected, have the same value of EMF and have the same value of internal resistance. So, N, let's say N is the number of identical cells connected. So, equivalent EMF we have already studied how to calculate the equivalent EMF. Equivalent EMF, this will be given by adding all the EMFs, E plus E plus E, all the EMFs that are present up till whatever is the number of EMF. Let's say N is the number of the cells that are present. So that becomes what? NE, N multiplied by E. Just wait for 2 minutes. All right. So equivalent EMF will be given by E plus E plus E and all the number of cells that are present. Similar to the equivalent internal resistance, if we have to find out equivalent internal resistance. So R equivalent will be given how? R plus R plus R plus R. So if N number of cells are there, what will be the equivalent internal resistance? Anyone?
NR.
NR. Yes, right. So this will be R plus R up till NR will be the equivalent internal resistance. Now, external resistor is fixed. We are just talking about the internal resistance of the cell. We're just focusing on identical cells right now. So external, don't go on the external resistor. External resistor, you people know how to solve it. External resistor, you have seen all the circuits, how to solve different methods to solve. Kirchhoff's law also you have studied. So R equivalent you people can easily find out, even if the circuits are complicated. Main thing, if identical cells are given to you with these similar EMFs and similar internal resistance, then you call it as identical cell. Unidentical we have seen. Why are we specifically discussing in identical cells? Because your calculations become easier if you have the direct formulas written. So current formula of current. So formula of current, this will become yes, what is the formula of current? Hamza?
Ma'am, I is equals to V by R.
V by R. So what is V in this? Hamza, try. See what is the voltage that you are able to see. See, Hamza, what is the EMF? So what is the equivalent EMF? Look at the screen, it's
N.
written N. Exactly. So I will be, this is N and this is E. Now, external resistor in divided by R you said. So total resistance you have to take. Internal resistances as well as the external resistor that is given. So this becomes what? External resistor is given as capital R. Internal resistance is NR. This is the formula of current. Internal resistance versus external resistance. Now you have two major cases. Let's discuss first case 1. Case 1 says if somehow your external resistor is much greater than your internal resistance. See, what is our denominator? Our denominator was NR plus capital R. So if capital R is so huge, addition of NR won't have any effect on the answer. It's like capital R is 1000 and small nr is so small, it's almost equal to 1. So 1000 in comparison to 1000 is very much greater than 1. So if you add 1 to 1000, that will give you 1001. So you will say 1001 is almost equal to 1000 only. It means nr plus r. Capital R means external resistor is so much greater than the internal resistance that you can say the sum of both of these will almost be equal to what? Capital R. So what does the formula of current now look like? NE will remain the same. Instead of this denominator that we had previously, it will be only capital R. So this is which case? So you people have to identify it by looking at the formula, by looking at the question. In the question, it might be given to you. Values will be given to you in the power of 10 to the power minus. If these values are given, then you can easily identify. Then your second case, case 2. If small r is very much greater than your capital R. See, what was the denominator? NR plus capital R. Now it's like NR is acting as that infinite or the 1000 bigger number. And you're adding just 1 or 0.5, such a small number to it. So obviously your denominator won't be affected. That quantity, all the sum of both of these will almost be equal to N small r. Reason? Because n times small r is so much greater. R is already greater than capital R. Now n times small r becomes so much greater than capital R that even if you add it, you would get the answer approximately around small n multiplied by small r. So now look at the formula. Formula of current was what? NE, and in terms of the denominator, what do we have to write? NR. So NN gets cancelled. Current is equal to EMF divided by the internal resistance of the cell. All right, this is the series connection. First, note it down. If you have any doubts over here, just ask me. Then we'll do the and discuss the parallel combination one. Now, in order to just distinguish from the number of identical cells that we took, no, small n, number of identical cells, let's take the number of rows, identical rows that are present as m, so that we won't get confused with small n. And even if I take this as n, then it would be confusing. Parallel combination n is there, or series combination is being considered. So let us take it as m only, m identical cells in parallel. M identical cells in parallel. This is also E, this is smaller. So equivalent EMF. All of you write me in the chat box, what should be the equivalent EMF of this combination? All of you. What should be the equivalent EMF? Sarah, Atif, who else? Only Sarah and Atif. Huzaifa, what should be the answer? Krishna. Equivalent EMF. Krishna. Okay. All right. And who else? Only 3 students have answered. Fatima, you try. What should be the equivalent EMF? Huzaifa, what is E1, what is E2, what is E3? There's nothing given to you as E1, E2, E3, no? All the cells are identical. E divided by E, that is 1. So only Atif has given the correct answer. No, not the calculation part, also. Not the calculation, by just looking at this equivalent. Only Atif has given the correct answer, that is E. These are parallel combination. Why would the EMF change? Voltage remains constant in case of parallel combination. So it won't be M divided by E as well, Krishna. It will directly be E. E equivalent will be E. So E equivalent, this will be capital, because this is a parallel combination. Now internal resistance will be what you were mentioning, Krishna. Internal resistance, and that is calculated. The method that you were telling, Huzaifa, 1 by E1, 1 by E2. That is not how we calculate the voltages. This is how we calculate the resistors which are connected in parallel. So all these resistors are connected in parallel. So R equivalent will be what? 1 by R plus 1 by R up till M times. So 1 by R equivalent can be directly written as, this can be written as 1 by R equivalent. This can be written as M by small r. So R equivalent becomes what? This becomes R divided by small r. Yes. So we have equivalent internal resistance, we have equivalent EMF. Let's calculate current. So current becomes what? Current will be E divided by capital R plus M by small r. So this will be what? If we take the LCM, this is R by small m, no? R by small m. It's R by small m. So M gets in the numerator as well. So this becomes M capital E divided by, M gets multiplied with this capital R plus small r on taking the LCM. So this is the formula of the current that you get. Now again, you will be having both the two cases that we have studied. Two cases as in when your capital R is greater than small r, when your small r is greater than capital R. So case one, let's say capital R is very much greater than small r. So M times capital R plus small r. Hanifa, tell me, how can we write this? What is this almost equal to? Hanifa? Capital R is very much greater than your small r. So this approximation is almost equal to, if
R,
2, yes, sorry, Hanifa.
R,
Capital R.
no.
Capital R with M also. Because M is also there, no? So this will be MR. Yes, Josefa. Right, it is MR. So current was what? Current was ME, that is divided by, now the denominator is M capital R. So MM gets cancelled, current is E divided by R. This is the first case that you get. Then you have the second case. In case of second case, you have small r greater than capital R. Small r greater than capital R means what? Your internal resistance, this is greater than your external resistance. So here, M times capital R plus small r. This is almost equal to what? Sarah? Yes, small r. This is almost equal to small r. So current was ME divided by this whole term. Now we can write it almost equal to small r. So this becomes the current. Remember, if your internal resistance is greater than the external resistance, means this case, parallel combination is preferred. Parallel combination is preferred. And if your external resistor is greater than your internal resistance, means this case, then we consider series combination. Series combination. So this comes in the exam. This question comes, which case you will prefer. So you will take out both the cases, that we'll do also, numericals also we'll do. First note down the parallel case, then we'll do a numerical. So your rest of the doubts will get clear. Even if you have any doubt, just ask me. All of you try this question. Formula based questions is whatever we have studied just a few minutes back. And all those who get the answer for the first, second, third part, just write one and submit your answers in the chat box as you people keep on getting your answers.
Ma'am, you should find the current in the circuit, right?
Teacher, we should find the current, right?
Did you people get the answer of any of the parts?
Teacher, the question is vague. We should find the current in both series and parallel combination.
In parallel. Find out in parallel. See, find out both the currents in case of parallel combination. Take the first part in case of parallel, take the second part in case of series, because you have to identify why are we taking it in case of parallel or series. See, the third part says what, decide which combination which you would prefer. Don't take it as a third part, just take it as a part of this question only. Now you people will be able to get the answer of the first part or the second part. See, you have to decide which combination you have to prefer to get more current. So check for external for first part, parallel combination is preferable or series. Obviously you will realize that parallel combination is preferable. So this is how you have to solve this question. So leave the third part as a separate part, because that will be utilized in the calculation of first and second only. So in the question, it won't be given to you directly whether it is parallel or series. First part, Hamza and Hamza, Josefa, Krishna, Sarah. No, that's not the correct answer. Second part, no Hamza. Second part, Krishna, no. Almost you people are right, Krishna and Hamza. Second part will be this, but your first part is not correct. See, Krishna, that you are answering no third part series combination. See, external resistors value is given. One value is given to you as 0.05 ohm. Second value is given to you as 100 ohms. Now check the conditions. I have made you write which parallel combination you should prefer, where series combination you should prefer. So when you see capital R is greater than small r, then which one you should use, parallel or series? Then see the second part. Is capital R greater than small r or small r is greater than capital R? Then use it. Atif's answer is perfect. First part, Atif's answer is correct. Second part, Sarah, yes. Second part, Sarah is also right. First part, others also try. Atif, your answer is right. Atif, try the second part. See, that's why I have erased the third part from this. By mistakenly, I have written the third part. Basically, series parallel combination has to be decided by the value or by just looking at the value of external resistor. Try the first part also. At least Hamza, Sarah, Krishna, try again. Krishna, don't take it as a series combination for the first part. What about others? Fatima, Hanifa, Hiba, Kulsum, you people also try. See which case you should prefer, where capital R is greater than small r. Is it happening in the first part? So you should prefer series or parallel combination. Which one? Second part, Atif, yes. So both the parts have been solved. No, Sarah, first part is incorrect. Fatima, answer of second part. No, slight mistake. You people have to also mention, no, which combination you people are preferring. For example, is it parallel or series? First, 39 amperes. No, Krishna. Also mention which case you are preferring. Parallel combination, series combination. Then only you will be able to get the answer, no? Last 1 minute and we'll discuss this. So others also try it quickly. First part, no. See, combination which you have taken, Sarah, that is right. But I think your calculation error must be there. Josefa, yes, combination you have taken it correctly, Josefa, good. But Josefa, now solve it also. Find out the value of current. Combinations you have identified it correctly, but now solve it. Formula is given to you. We have discussed the formulas. See, let's discuss it then only. Krishna, Sarah, and all those who were getting answer like 16, and all those Sarah and someone else also answered in this way. Yes, Sarah was also getting 16. See, you people have to not round it off. Parallel combination you are preferring. External registers value is given to you just to check which combination which you will prefer. Like, let's talk about the first part. First part is what? First part is number of identical cells is 8. Internal resistance is 1 ohm. External resistance is 0.05 ohms. So small r is very much greater than capital R. This shows that you have to prefer parallel combination. This data is given to you in order to check whether to prefer parallel combination or series combination. Now, once you have the combination, you have to solve it the way you have the formula for parallel combination. Formula for parallel combination is ME divided by R plus M into capital R. That is to check if the question specifically says to you, check it for parallel combination, then you can round it off. All right, right now you have to utilize the whole formula for the calculation. So if you put in the formula, m's value is given to you 8 identical cells are given. So 8 into emf was what? 2 volt, no? 2. Small r was 1 plus 8 into capital R was 0.05. So this will come around 11.42 amperes. Now second part. Second part is what? Second part, R will be 1 ohm, capital R. This is given as 100 ohms, I believe. So here capital R is very much greater than small r. So what do you prefer? Which combination you have to prefer? You have to prefer series combination. Now, once you have series combination, you know the formula for series combination. I is equal to NE divided by N small r plus capital R. N is identical cells, number of cells is 8. So N is also 8. 8 into 2 volts divided by N is 8 multiplied by 1 plus external resistor is what? 100. So this becomes 16 by 108. So this will almost be 0.148 ampere, I think. Just check it once again. Is it 0.148 or 0.16? Around this will come. This is how you solve these kinds of questions. One last small concept is left in this, that is mixed grouping. Series and parallel combined together, that we'll see. But first you note down the solution of this.
Ma'am, can't we neglect 0.05 as R is small?
Yes, we can neglect, but if the question directly asks you to write about the parallel combination, here it has given you preference. You have to decide whether it is parallel or series. Just to use this formula. This is the hint given. If the question specifically mentions to you know that this is the case given, calculated, then you can neglect it.
Okay, ma'am.
in mixed grouping, you have series combination as well you have the parallel combination of all those series combination. Cells are connected in series combination, then they are further connected in parallel combination. So let's just ignore first the parallel combination, the rows that are there. Let's just see in one row, one single row, net EMF in a single row. Net EMF in a row. Just this row I'm considering right now, not any other row. Let's say n number of identical cells were connected over here. If n number of n identical cells are connected, so in each row, the EMF, what will be the net EMF?
Any.
Any. It will be any. So E equivalent will be NE. Similarly, R equivalent will be N multiplied by small r. So this is for what? This is just for a single row. Now we have reduced this row as this with internal resistance as this. So it means each of the rows will be having this value. So how would the circuit now look like? Now you have NE connected with NR. Then you have NE connected with NR. Similarly, you have NE, which is further connected with NR and your external resistor. Why? Because we have reduced this. We have found the equivalent EMF of all these. So obviously, this will how it will look like. Now the parallel combination. See, NE is the net EMF of the whole series. So what will be the equivalent EMF now of this combination? Anyone? Atif, you can answer.
Any.
N. Yes. See, capital E was the EMF in the last case of all those. Now this is NE. So NE parallel in the parallel combination, NE will remain the same. Potential remains the same in parallel combination. No. That's why if the voltage is right now NE of one cell, it will be NE for the entire. So that's why we'll take the equivalent as N capital E. But in case of equivalent internal resistance, R equivalent, this time it will be calculated by 1 by NR plus 1 by NR up till, let's say M rows are there. N cells in a row and M is the number of rows. So this becomes what? M times, which 1 by R equivalent is what? M by NR. So R equivalent becomes NR divided by M. This is the first thing that you have to remember. Why are we considering NR and M? Why are we considering NR and M? See, in case of mixed grouping, first we have, how do we solve series and parallel combination? First, we identify whether they're connected in series or they're connected in parallel. We have identified that this combination of cell, this group of cell, this is connected in series. So we have reduced this into N capital E with N into small r. And all these are now further connected in parallel combination. So parallel combination, how do we solve? How we solve parallel combination? Voltage remains the same. R equivalent is given by the reciprocal sum of all these. In case of series, how did we divided by R equivalent plus capital R. So E equivalent is NE. R equivalent we have found that was N small r by M plus capital R. So M will be taken in the LCM. So this becomes MNE divided by N into small r plus M into capital R. Now, just for your clarification, small n, this is the number of cells in a row, whereas M is the number of rows present. So don't get confused between N and M, and don't replace it Don't multiply m with small r or n with capital R. Whatever is specified, just multiply it with that. N is taken as number of cells in a row, m is taken as the number of present. And one thing that can come in examination, now it is not included, if your current is maximum in only one condition. The condition is that n into small r gets almost equal to m into capital R. This is the condition. All right, so just note it down. Mixed grouping, case of series and parallel combination which are connected together. At any step, if you people are having any difficulty, just ask me. Is this clear to you people?
Yes, teacher.